Welcome to The Explainer. Today, we are taking a fascinating deep dive journey into the very heart of electricity for your Cambridge AS and A-level physics exams. Specifically, we're tackling syllabus 9702, and we are going to look at this like master architects. You see, every year I watch thousands of students completely crumble when they face these electricity questions. You typically have two types of students. First, there's Alex. Alex overloads every answer with raw physics facts, writing massive paragraphs, but completely misses the actual analysis the examiner is looking for. Then there's Sam. Sam rushes in, completely ignores the command word requirements, misses the critical nuances, and bleeds marks everywhere. Today, we are going to fix that. We'll start with the everyday macroscopic concepts of circuits you might already think you know, and then zoom way down to the microscopic level of atoms and electrons. By the end of this, it's not just about knowing the formulas, it's about designing your answers like a structural masterpiece so you can secure every single mark. Let's get started.
Okay, let's dive into this. Here is our roadmap for today's session. First, the foundations of electricity. Second, inside the conductor. Third, energy, power, and resistance. Fourth, component characteristics. And finally, resistivity and material properties. This is your cognitive scaffolding for mastering the exam.
Section 1. Foundations of Electricity. The Basic Toolkit. To build complex engineering masterpieces, we first need a rock-solid grasp of our basic vocabulary tools.
Let's make sure our fundamental macroscopic concepts are absolutely locked in, because this is where Sam always loses easy points. First up is charge, measured in coulombs. Think of these as actual quantized bits of electricity. The absolute smallest we generally encounter being the charge on a single electron. Next is current, measured in amperes, which is simply the rate of flow of these charge carriers. Notice the word rate there. Examiners love that. Then we have resistance in ohms, which is exactly what it sounds like, the physical opposition to that flow. If you got to state what is meant by a command word on the exam for any of these, you have to be precise. You can't just say current is moving electrons. You need to say rate of flow of charge carriers. But I really want to draw your attention specifically to the next concept because this is a classic trap.
The crucial point is potential difference, or voltage. Cambridge loves to ask you to define this for 2 marks. If you're Sam, you might write, it's the voltage pushing the current, and you'd get 0 marks. The correct architectural definition is the energy transferred or work done per unit charge as it moves between 2 points. This is beautifully expressed as V equals W over Q. This isn't just an abstract equation. It is the core concept that directly links the invisible flow of electrical charge to actual physical work and energy in the real world. It tells us how much push or energy each coulomb of charge carries with it. Before we continue, subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Seriously, doing that ensures you won't miss these critical mark-saving definitions.
Section 2. Inside the conductor. The microscopic view. Now we transition from the macro view of circuits right down into the actual microscopic lattice of a wire. When you flip a light switch, the light comes on instantly, right? So it's incredibly tempting to think electrons are just zooming through a wire at light speed. But that is a massive fundamental misconception that examiners will penalize you for. When a circuit is completed, the electromagnetic wavefront, the signal itself, moves at nearly the speed of light, 3 × 10⁸ meters per second. But the actual charge carriers, the physical electrons, they literally crawl at a microscopic drift velocity of roughly 0.1 millimeters per second. Why? Because they aren't in an empty tunnel. They are constantly, violently colliding with these stationary, vibrating positive ions in the metal's crystal lattice. It's like comparing the speed of a loud shout moving across a crowded room versus the speed of a single person trying to physically push their way through that exact same crowd. One is a wave, the other is a particle. Keep that distinction crystal clear.
And this brings us to a brilliantly illustrated slide that shows exactly how we visualize this. This derivation is a staple in the 9702 syllabus. We are looking at a specific volume of charge moving through a segment of wire over a given time, labeled T. We have our cross-sectional area A, and N, which is a super important term, the number density of charge carriers per unit volume. Don't confuse N with total number. Each carrier has a charge Q, and they are all moving with that incredibly slow average drift velocity we just talked about, V. By visualizing this physical cylinder of moving charge, we can actually build the macroscopic formula for current from these microscopic properties. This is where Alex usually just dumps the final formula on the page and loses all the derivation marks. We are going to do it the right way.
I'm going to put 60 seconds on the clock in your mind. Let's walk step by step through this logical, mathematical derivation so you can lock in all 3 or 4 marks. Step 1. In time t, a charge carrier moving at velocity v covers a distance L. Basic kinematics tells us distance equals velocity times time, so L equals vt. Step 2. The total volume of this shaded cylindrical section of moving charges is the area A times that distance L, so substitute that in, and volume equals AVT. Step 3. To find the total actual charge in that volume, we multiply the volume by n, our number density, and q, the exact charge of each single carrier, so total charge equals ANVTQ. Finally, step 4. By definition, current I is simply total charge divided by time t. When you divide ANVTQ by t, the t cancels out beautifully, leaving us with our final blueprint equation, I equals ANVQ. You just connected the invisible microscopic world directly to the macroscopic current on your multimeter. That is a perfect, structured response.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, Section 3. Energy, Power, and Resistance, the Mathematical Core.
Let's zoom back out. Here's your essential time management matrix for equations. We've already established charge is current times time, and voltage is work over charge. Power, which is the rate at which work is done, is voltage times current, P equals VI. And resistance is voltage over current. But I want you to seriously look at those last 2 bullet points. By taking the resistance equation, R equals V over I, and strategically substituting it into the power equation, we unlock 2 incredibly useful variations. Power equals V squared over R, and power equals I squared R. Why does this matter for the exam? Because if you have a series circuit, current is constant, so using I squared R makes comparing power dissipation a breeze. If you have a parallel circuit, voltage is constant across branches, so using V squared over R is your fastest path to the answer. Choosing the right tool saves you time, and time equals marks. Which brings us to the absolute grandfather of electrical physics, Ohm's law. If Cambridge asks you to state Ohm's law, Sam usually writes V equals IR, 0 marks. The correct architectural statement is this: the current through a metallic conductor is directly proportional to the potential difference across it. But pay close attention to that final condition, provided the temperature remains constant, or physical conditions remain constant. If you drop that last phrase, you drop the mark. That condition is absolutely critical because, as we're about to explore, temperature almost never remains perfectly constant in the real world of circuits.
Section 4. Component Characteristics, Real-World Behaviors. Not all materials obey Ohm's law perfectly, which makes them fantastic subjects for exam questions. Welcome to our interactive data scan challenge. Look at these IV characteristics. These are graphs of current on the y-axis versus voltage on the x-axis. Notice how striking the differences are. On the top left, the metal wire gives us a perfect ohmic, straight line through the origin. Current is strictly proportional to voltage because temperature is mostly constant. But look below it at the tungsten filament lamp. It curves. It's non-ohmic. As the voltage increases, the gradient of the line actually decreases. In an IV graph, a decreasing gradient means the resistance is increasing. Why is it fighting back? Because that tiny filament is getting incredibly hot, sometimes up to 1500 degrees Celsius.
Now for the Find the Flaw challenge. When asked why resistance changes, Alex often writes a huge paragraph saying, "The heat makes the electrons bump into each other more." That's flawed. Here is your perfect framework. For a metal filament lump, increased temperature means the positive ions in the crystal lattice vibrate with much greater amplitude. This creates a much larger collision cross-section for the flowing electrons, significantly reducing their drift velocity. So, more heat equals more resistance. But look at the thermistor. It's a semiconductor. Semiconductors have very few free electrons to begin with. When you add thermal energy to a thermistor, that energy actually overcomes atomic bonds and frees up thousands of new electrons to act as charge carriers. The increase in the number density, N, completely overpowers the increased lattice vibration. So, amazingly, for a thermistor, more heat equals dramatically less resistance. That is the kind of high-level explanation that secures top marks.
And right here we have the diode, another semiconductor marvel. We're going to do a speed writing challenge in your head right now. How would you describe this in a single perfect paragraph? Notice how this curve isn't symmetrical at all. In the reverse bias, the negative side, it acts practically like a solid brick wall, letting basically zero current pass. But in the forward direction, once the voltage reaches a very specific threshold, say around 0.6 volts for a standard silicon diode, it suddenly shoots up. It conducts with very little resistance. It is literally a one-way electrical gate. Understanding and being able to quickly sketch this exact curve is foundational, not just for the exam, but for almost all modern digital electronics.
Section 5. Resistivity and material properties. How do we standardize all of this? To understand a material's intrinsic resistance, you need to decode the variables. Think of water flowing through a massive pipe. Resistance is directly proportional to length. A longer wire means more collisions for the electrons over a greater distance, just like a longer pipe means more friction for the water. Resistance is also inversely proportional to the cross-sectional area. A wider wire means a much broader path, so more room for electrons to flow freely, just like a wider pipe lets more water through. Now, the constant that magically ties these proportions together is ρ, the resistivity. Remember, resistance applies to a specific object, like a piece of wire. But resistivity is a fundamental property of the material itself, whether it's copper, gold, or nichrome. This gives us our absolute master equation, R equals ρ times L divided by A. If you can manipulate this, you are golden.
This brings us to our final system challenge. By using the exact blueprint formulas we just covered, you could calculate that it takes exactly 10.4 meters of nichrome wire to engineer a perfectly rated 48-watt heating coil running on 12 volts. Abstract physics suddenly becomes concrete, world-building engineering. If you can precisely control energy, power, and the microscopic flow of electrons just by calculating the exact length of a wire, what other incredible things could you design? Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.